Physicists, welcome to video 2 out of 3 of subtopic 7.3. And in this video and the next, I'm going to talk about particle physics and elementary particles. At first, it's going to kind of seem like maybe a bit of an oddball topic. Doesn't really fit in anywhere. And in fact, that may be true. But really, the reason why this is a core topic is because this is at least the immediate future of physics. This is where the research funding is going right now. And this is where the big discoveries are going to be made, certainly in your lifetime, will be in this field of physics. And it's also intimately tied in with astrophysics, as we'll see a little bit later, all right? Now, to understand the study of elementary particle physics, we have to step back about 100 years ago and think about the state of physics in the first third of the 20th century, okay? Now, at that point, it was thought that all the building blocks of matter had been discovered. Protons in 1920, neutrons 32, electrons 1897. Electrons were the first of these 4 to be discovered, and then photons in 1905. So it was thought that, okay, we've already figured this out. These are the building blocks of matter. There's nothing smaller than these 4 particles, all right? But this proved to be completely wrong. By the middle of the 20th century, hundreds of other smaller particles had been discovered. And in fact, even today, smaller particles are still being discovered, okay? And this is what's called particle physics, okay? And the way that these were discovered is by using particle accelerators, all right? And these are long, vast sort of tunnels, usually underground, that produce high-speed collision. There are more than 30,000 particle accelerators operating in the world, and they use electric fields to accelerate particles to nearly the speed of light, and they contain them in very, very tight beams. And some of the most famous ones are CERN in Geneva, Switzerland. There's the Stanford Accelerator in California, Fermilab, New York, Illinois, all these particle accelerators, okay? Now, these are also sometimes called atom smashers, which is kind of not really a scientifically accurate name, but you hear that. Those are particle accelerators. The whole field is called particle physics, okay? And the model that I'm going to describe to you in the next few videos is called the Standard Model. You need to know that term. That's a very important term, okay? Now, an elementary particle is a particle that's not made of any smaller components. They're the most basic constituents of all matter. And as I said before, in the early part of the 20th century, physicists thought that they had figured out what the elementary particles were. They thought they were electrons, protons, neutrons, and photons, okay? Now, high speeds are needed to determine to discover or to sense these elementary particles. There's a lot of energy to smash protons, neutrons, and electrons, and most of these are highly unstable, and they only exist for a tiny, tiny, tiny fraction of a second, and there are hundreds that are known to exist. So as an example, if I collide 2 protons, okay, one with high energy and one at rest, okay? And remember, the proton coming in is going near the speed of light. It's going really, really, really fast. This collision produces an entirely new particle, which is right here, and it's called the neutral pion, which we'll study a little bit later. And that particle is smaller than a proton, okay? So we've already debunked the myth that the proton is one of the elementary particles, okay? And the neutral pion lives for about 10 to the minus 16 seconds, all right? And then what that particle does is it decays into 2 photons, okay? All right, and since the pion did not exist before the collision, it was created from part of the incident proton's energy. So this is one of many, many, many examples of how an elementary particle is actually created. All right, now I'm going to throw a lot of different vocabulary to you that you probably haven't heard. And to help you keep it all straight, I provided a sort of elementary particle cheat sheet, which you're going to probably want to print out and put in your notebook as soon as possible to help keep track of all this stuff, all right? You're also going to want to pay attention to what the IB data booklet gives you, what's provided and what's not, and what you're going to have to memorize and so forth, okay? Turns out that all particles are either leptons or hadrons, okay? And there's 6 different kinds of leptons, all right? And these are elementary because they show no internal structure, but there are hundreds of hadrons. And if they have an internal structure and they're made up of much smaller particles, therefore they're not elementary, okay? And the particles that make up these hadrons are called quarks, okay? So the elementary particles are, okay, number 1, exchange particles, number 2, quarks, and number 3, leptons. And what we're going to do is we're going to go through each of these kind of particles in great detail in the next couple of videos, and you're going to be an expert on particle physics when you're done, okay? Now, in order to understand these three particles, we have to consider 4 fundamental forces in nature. And I know I've talked about how there are 3 fundamental forces in nature. There are actually 4, okay? When I was talking about 3 before, I said gravitational, which was the first kind of force that we studied, electromagnetic or electrical forces, and I said that there was a nuclear force. I referred to it as a strong nuclear force. Turns out there's a weak nuclear force. And we have to, in this topic now, we have to differentiate between the strong nuclear force and the weak nuclear force. And this is an interesting table because it tells you the relative strength between 2 protons in a nucleus, okay? So here's your 2 protons in this nucleus right here, here, and here, okay? Notice that the gravitational force, as I've said before, is by far the weakest force, okay? And the nuclear force, the strong nuclear force that holds the nucleus together, is by far the strongest one, okay? All right. So let's take it in pieces here. Number 1, exchange particles, okay? All right. Now this is going to get kind of weird, and it's really cool, and you guys are probably going to want to talk about this a lot in class, and I got all the time in the world to talk about it, okay? Now, remember that we said that electromagnetic waves were a combination of E fields and B fields, and the E fields and the B fields are perpendicular to one another, okay? All right, and the resulting force from electromagnetic fields is therefore really the sum of the magnetic field and the electric field. We call this the electromagnetic force, okay? Or at least we're going to call it the electromagnetic force. Remember, we also only considered the electric field when we were talking about things like polarization. And that's because the electric field is much stronger than the B field in an electromagnetic wave. But here we're going to consider them both, okay? Because both electric fields and magnetic fields produce force on charged particles, right? Now, the electric field, the electric force and the magnetic force act over a distance with no contact involved. Okay, remember we didn't, you basically throw a charge in a field and it doesn't have to actually touch the thing that's making that field, right? So, for example, a charge and another charge's E field, or moving through a B field, it's going to move. So in an E field, it's going to move in a parabolic fashion. In a B field, it's going to move in a circular fashion. And we've studied all this before. And the question is, how does it know that the other charge is there, okay? Not only that, is the effect instantaneous, right? So we talk about a distant star exerting a gravitational force on us right now. The effect of that gravity, does it take place instantly? Because if it did, it would violate the laws of physics in the sense that nothing can act or move faster than the speed of light. And we've talked about this a little bit in class. It's kind of a great TOK question, all right? Anyway, these are really interesting questions. And so particle physics seeks to explain this, okay? All right, and it seeks to explain it in the sense that we have to think of electromagnetic waves as photons, as particles, and we've studied this, right? Okay, all right. Particle physics says that the force, all of these forces, is transmitted in a field that goes through these particles, okay? So, for example, in the case of photons, all right, they're saying that it says that the force is transmitted through photons. If that makes sense, okay? It's going to make a little more sense. Think about this. If you have 2 children on roller skates with 2 heavy pillows, okay? When they throw them to each other, each child is pushed backwards. There's a repulsive force, right? Okay? When they, if they hold them and the other one pulls the other one, they're going to be pulled together, an attractive force. In both cases, the force is exchanged through the pillow. Without the pillow, okay, you would not have the force between the 2 children. So in this sense, the pillow becomes the sort of the mediator of the force, okay, or the medium through which the force is transferred between them, okay? It's very much like that in particle physics, okay? Except for there are different other objects, these exchange particles, that actually transfer that force. Now, for the electromagnetic force, it's the photons that are exchanged between two charged particles that give rise to the force between them. This is a huge shift in the way of thinking of what we've been doing before in this class, okay? So therefore, the photon is what we call an exchange particle, and it transmits the electromagnetic force from one object to another. And in broad terms, the term exchange particle refers to an elementary particle used as an intermediary of an interaction. It mediates or carries the force, okay? All right, so for example, if we consider two electrons, okay, and they're pushed apart by an electrical force. I bring the black electron in, I just let it go, it's going to fly off, right? Okay. We can actually represent the interaction of between the two electrons pictorially, okay? And this is really cool, okay? So here are the two electrons, all right? The two electrons, okay, before I talk about this, I should talk about, in these kinds of diagrams, which are called Feynman diagrams, time goes from left to right, okay? So you can see earlier in time, I have two electrons, and they're coming close together. So you can think about distance as being on the y-axis, okay? This is the simplest way to explain a Feynman diagram to you. They're more complicated than this, but nevertheless. And when they come together, there's going to be a force of repulsion, okay? Well, according to the theory of particle physics, the photon has to be exchanged between them in order for there to be a force felt by one electron on the other. And it would be represented by this. A photon is always represented by a wavy line, okay? So at this point, they fly apart. There's a force between them. And then the electron goes this way, and then the other electron goes that way. This is called a Feynman diagram, and it's something that you need to know. So, in other words, what's weird here is that one electron will emit the photon and the other one absorbs it. And the photon is the force carrier. It's the carrier of that force. Without the photon, there would be no force between them. They would not be able to interact, okay? The photon also carries momentum, so the momentums of the electrons change, so they have different paths, but that's a whole different issue, okay? All right, you got this? This is cool. It's going to get even cooler, all right? Now, for weak nuclear interaction, there are three exchange particles, okay? All right? There's the W particle and the Z particle, and there are two different kinds of W particles. There's W plus and W minus. Whenever you see a minus, whenever you see a minus relative to a plus, okay, that's the antiparticle of that particle. So if you start off with W plus, that's the particle. That's the exchange particle. Its antiparticle would be W minus, okay? And then Z is just denoted by Z0, okay? And these are in a group called the gauge bosons. And the other gauge bosons are photons and gluons, all right? And here's some interesting data on the gauge bosons, okay? And this is sort of summed up in the elementary particles cheat sheet that I'm going to give you. So don't worry too much about this. You don't really need to worry about the rest mass or the lifetimes, okay? We're going to figure out what all of these other variables are in just a little bit, okay? So note that unlike photons, they actually do have mass and they have extremely short lifetimes, okay? All right, and each of the four fundamental forces has its own different exchange particle, okay? So we've studied photons and we've studied gravity. It turns out that the exchange particle for gravity is called the graviton, which is kind of cool. We haven't talked about that before, but that's what it is, all right? Okay, now, for the weak nuclear force, we have quarks and leptons only. For the strong nuclear force, we have hadrons, and I'm going to introduce these terms to you, okay? Here are your gauge bosons, which I just talked about, okay? All right, and what's interesting about this is it really causes us to kind of sit back and think about this question, what is a force? Well, we now have to think about a force as the exchange of particles, okay? And from your IB data booklet, they essentially give you all this information, but in a slightly different format, okay? So make sure that you refer to what's given to you in your data booklet and get familiar with that, because there's a lot of stuff that you'd have to remember otherwise with this topic, okay? Now, I want to talk a little bit about the Higgs boson. This was the missing link that was late to be experimentally verified. It was actually fairly recently in 2012. It deals with mass. In particular, it's the exchange particle that makes it possible for mass to exist, so it's obviously related to gravity. Without it, the standard model disintegrates mathematically. It's responsible for the masses of all the particles in the standard model. And what's cool about the Higgs boson, why it's such a big deal that it was discovered, is that it may be the first step in discovering dark matter. And dark matter is a substance that is believed to account for around almost all the matter in the universe. And what's weird about it is that it's undetectable. It doesn't interact with electromagnetic radiation. It hasn't been directly observed, but its existence and properties are inferred from various gravitational effects, such as gravitational lensing through the Hubble Space Telescope when we look at distant galaxies and so forth. Okay, second elementary particle I want to talk about are quarks, okay? And quarks were first proposed by two physicists working independently around the same time in the early 1960s, Murray Gell-Mann and George Zweig, okay? And there are 6 different types or flavors of quarks. We have the up quark, which is U, charm quark, C, top quark, T, and then we have the down quark, the strange quark, and the bottom quark, okay? Now, these names are kind of funky, obviously. I actually kind of like the fact that they're given such colorful and imaginative names. I really like that in physics when we discover something new and it's got, it's imaginative and kind of fun and kind of colorful. But you need to know that the charge of the up charm and top quarks is positive 2/3 of the elementary charge, and of the down strange and bottom, it's negative 1/3 of the elementary charge. Okay, and again, this is on your cheat sheet that I'm going to give you. And the antiparticles of all of these also exist. So there's really 12 different kinds of quarks, right? Okay, and we denote the antiparticle sometimes by a minus sign, but more commonly by a bar above it. Okay, so U bar, C bar, T bar, D bar, S bar, and B bar. Okay, and remember that the particles that make up hadrons are called quarks. Okay, quarks only make up hadrons. Okay, all right. Now, there are only 2 types of hadrons, okay, and they're called baryons and mesons. And a baryon is made up of 3 quarks, okay? If you have 3 antiquarks, it's an antibaryon. Mesons, on the other hand, are made up of 2 quarks, and one of them has to be an antiquark, okay? Now, this is what the IB data booklet is giving you, okay? So they're giving you the charge of the basic quarks, okay? And quarks only occur in hadrons. Quarks cannot be isolated. You'll never find a free quark floating around in the universe. It just does not happen, okay? It's kind of like you're never going to find a north pole of a magnet floating around without a south pole. Kind of the same thing. So some examples of hadrons. It turns out that a proton is a hadron, and specifically it's a baryon. And it's made up of 2 up quarks and 1 down quark. And we call this UUD. Okay, all right, so you can figure out the charge of a proton. You already know that the charge is positive QE. Well, when you work out the math, you have plus 2/3 plus 2/3 minus 1/3, and that gives you 1. So that works out. Neutrons are also examples of baryons, and they have no charge, as you know. Their quark content is DDU, and when you do the math, you find that negative 1/3 minus 1/3 plus 2/3 is 0. So it works. It works out, okay? Okay. Here are some examples of mesons. So pi meson is one that you're going to need to become familiar with, okay? And that's 1 up quark and 1 anti-D quark, and this D has a bar over it, which is kind of hard to see, okay? All right. And that's a pi meson, okay? And the electric charge is positive QE, all right? Let's see. The antiparticle of the pi meson is a pi negative, and that's got the anti-U and the D. So it's just the opposite of what this one was, and you see that the electric charge is negative QE. Okay. And there's also the pi 0, which has no charge whatsoever. Whenever you see a particle that has a 0 as a superscript, it means that it doesn't have a charge. It's electrically neutral. A couple of notes about antiparticles. So the antiparticle of some particle P has the same mass, but is opposite in all other properties, okay? It's indicated as P minus and P plus, or P and P, sometimes, okay? And some particles have antiparticles which are identical to themselves, such as the photon. Okay? All right. Now, aside from electric charge, quarks have yet another property. It's called the baryon number. Every quark has a baryon number of positive 1/3, and every anti-quark has a baryon number of negative 1/3. And baryon numbers were originally sort of thought up because observed processes violated certain laws. So we have all these conservation laws. So in order to understand this initially very bizarre branch of physics, basically, physicists had to discover or make up new conservation laws, and the conservation of baryon number is one of them. So in all reactions, electric charge and baryon number have to be conserved. Now, to find the baryon number of individual hadrons formed by quarks, all you do is you add the individual baryon numbers. So for UCT, it's going to be plus 1/3, plus 1/3, plus 1/3, which is 1. UD, right, and this D is an antiparticle, you're going to have 1/3 minus 1/3, which is 0. So it's pretty easy, okay? And again, this is what your IB data booklet gives you right here, okay? And I want you to note that quarks interact with strong nuclear, weak nuclear, and electromagnetic interactions, all right? Okay, so just to give you another overview, there are hundreds of hadrons, okay? But there are not hundreds of mesons. And the hadrons have lots of different symbols. Just a few: pions, etas, kaons, okay? These are mesons. And then baryons, lambdas, psis, omegas, deltas, okay? And all of this, if you look at your elementary particles cheat sheet, you'll see many more examples, okay? So let's talk about a couple of following decays, all right? I have a delta decay here into a proton and a negatively charged pion, okay? And then I have a I have a lambda decaying into a proton and the same thing. Now the delta 0 and the lambda 0 are two different baryons, okay? But they both have the same products on the decay. Now, the charge is 0 on both sides, and the baryon number is plus 1 on both sides. However, the first decay takes about 10 to the negative 25 seconds, and the second 10 to the minus 10. That's a huge difference in the amount of time it takes for these two decays to take place, okay? So it suggests different interactions. So it turns out that shorter lifetimes indicate a strong nuclear interaction, and longer lifetimes a weak nuclear interaction. It's important for you to note. I'm throwing a lot of information here at you in this video, and you're going to want to really rely on your textbook and the supplemental materials that I provide to you, okay? And there's one more property that we have to deal with, and it's called strangeness, all right? Okay? And it turns out that this lambda quark, this baryon, this has a strange quark, okay? Now, like baryon numbers, strangeness was originally conceived because processes violated certain laws, okay? So here's another, we have a conservation of strangeness. And in all strong interactions, charge, baryon number, and strangeness are all conserved, okay? If you have a situation where strangeness is not conserved, but everything else is, it's a weak interaction. Don't worry, we'll do lots of examples with these, okay? So, here's a nice chart that summarizes baryon and strangeness, okay? The strange quark is only the S quark, okay? Which is called strange. All the other ones have a strangeness number of 0, okay? And let's do an example to round out this video, okay? So the reactions below did not occur. If they did, a conservation law would be violated. Identify the violated conservation law, okay? All right. Well, it turns out that the baryon number here is violated. So you can see that if you look up on the tables, on the left-hand side, the baryon number is 0. On the right-hand side, it's plus 1, so the baryon number is not conserved, okay? Now, in this one, it turns out that charge is not conserved. So you just kind of have to go through and see which one is conserved, which one's not in each case. Electric charge is not conserved. One more example. Which of the 4 fundamental interactions through which did the following take place? Okay, so strangeness is violated here. Everything else is conserved, so this takes place through weak nuclear interaction.